Hey, welcome back, you guys. Let's take a look at exponential regression. So last time we talked about linear regression. Now we're going to do exponential. That's when it follows an exponential growth pattern. See the curvature to that data instead of straight line, right? Or maybe it follows an exponential decay pattern where it curves and decreases exponentially, right? Exponential decay. So let's go ahead and do an example there. We'll use our calculator to find the equation of the exponential curve of best fit as well. Okay, so it's called exponential regression. So here we're going to go ahead and go into Desmos and plot those points. Our time will be our x values in years. Our population there will be our y values. So flip this over. Let's go ahead and pull up Desmos.com. Go to the graphing calculator. We're going to go up to the left hand and click on table, left hand plus, click on table, and let's go ahead and put our years in. So it was 5, 10, and then 15. And then the population, the 5-year mark was 5,234,456. Does it not want me to do 5, 2, 3, 4, 4, 5, 6? The 10-year mark, it was 4,892,345. And at the 15-year mark, it was 4,012,345. Okay. Now, I would have to zoom way out to see this. So let's change our x-axis. Let's go from like -5 up to, I don't know, let's say 25 or so. And my y's, notice I go way up to 5 million something. So let's go from like -500,000 to, let's go to like 7 million. And you can kind of see, you can at least see those points there on the graph. Now it's hard to tell that it's an exponential decay function, but there's some curvature to that, and it does tell you in the actual example. It says use the exponential regression feature of your calculator. So let's go ahead and do that now that we have the data plugged in. We're going to go y1, and we're going to hit our tilde, and we're going to punch it in as a exponential. So a, b, and I'm going to go shift 6, so it goes to the exponent. So make sure that x to the 1 is an exponent. And then the second thing is you want to do is click this log mode. Now what you want to click that so it's in line with other graphing calculators, and it gives you the proper parameters for this. Enabling the log mode will change the strategy that it uses to fit the regression parameters. Okay, so by default, the regression parameters are chosen to minimize the sum of the squares of the differences. When log mode is enabled, it's a transformation that makes the model linear that's applied to both the data and the modeling in order to fit the parameters. Okay, so you want to click on that log mode. So again, y1 tilde a b to the x1. And then what you're going to do is we're going to make a note of that a right there and our b. So we're going to write, and we'll be able to write the equation. Y equals, put in the a and the b to that x power. Alright, so when I plugged in my x1, y1, and then I did the y1 tilde a b to the x1, it gave me the a was 6110389.82. My b is 0.973762. So you can now write the equation. Y equals 6,110,000, and we'll round to 390 on that, times b 0.7, we'll round that to the 100, 0.974 to the x. Now this is actually in terms of population is our y and time in years. So our population is to the t, right? So there's our population, or you can write a p of t is this, same thing. All right, let's look at this next one. We're going to go ahead and do the same thing. We're going to enter that data in and then write an exponential regression equation as well. So let me pull up Desmos and let's go ahead and enter the data. So I've entered all the data in with that upper left plus and entered it into the table. I adjusted my window just so you could kind of see the scatter plot there. Hopefully you can see that there's some curvature to that. And now we're going to plunge in our regression equation. So y1 tilde a times b to the x1 power, and then of course make sure you click on that log mode again. And then we're going to go ahead and note that and see how it goes through and models that data pretty well, right? So let's go back, enter that in right here. So it was y equals, my a was 82.94282 times b. My b was 0.836692 to the x power. Now this is in terms of population. P is our y value, and we'll go ahead and round that to 82.9, and we'll round this to the thousandths of 0.837 to the time t in years. There's our regression equation, exponential regression equation. Now it says, what is the decay rate? Well, you remember how we had a times 1 minus r to the t for something that's exponentially decaying, right? So what's my r? Well, if 1 minus r equals that 0.837, let me solve for r. So let me subtract 1 on both sides. I got negative r equals negative 0.163. Divide by negative 1 on both sides, so I get 0.163. So the decay rate is 16.3%. So the population is decreasing. Population is decreasing by 16.3% each year. Right? That's why it was curved like that, right? Decreasing, exponential decay, right? Decreasing by 16.3% each year. Now we've got this regression equation that we're going to go ahead and use on this last part. So what's the population? If we were to extrapolate or predict 20 years out, outside of our range here, what would it give us? So I go ahead and punch in that 0.837 to the 20th power and then multiply it by 82.9. Let me pull up our scientific calculator for that. Yeah, 82.9 I punched in times 0.837 to the, so I can either do shift 6 or click that a to the b power to the 20th, right? And that gives us that 2.3608. Push that in here. So 2.36, we'll assume this is in millions or whatever. This would be a great U-try problem. So if you want to go ahead, pause the video, go ahead and enter that data in as your x1 and y1. 0, 3, 5, 10, 15, 22, and so on, right? 4.63, da 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 da. And then model it. So here you got the data, and I zoomed out a little bit so you can see the scatter plot as well. Now we're going to go ahead and punch in y1 tilde ab to the x1 and make sure we click on that log mode right there. We're going to go ahead and note that and write our equation with the a and the b values given. Our a was 4.64495 times b, which was 1.08221 to the x power. So this is the value of our investment. We'll round it to hundreds there. We'll round this 1,000 after n amount of years. Okay, so 1.082 to the n. Based on the equation, at what percent rate is this increasing? Right? Remember the data was increasing exponentially. So you want to think to yourself, y equals a times 1 plus r to the t, right? So if I set 1.082 to 1 plus r, and I solve for the rate it's increasing per year, 0.082 is my r, so I got an 8.2% increase per year. That's what this investment is doing based on the data, all right? And now let's go ahead, and now that we have the value of the investment after n years, let's go ahead and plug that in and predict what that would be for 12 years. And we get approximately 11.95. So remember, this is in thousands, right? So after 12 years, the investment's worth approximately $11,950, right, in thousands. All right, so now we've seen stuff that models a linear relationship. We've seen stuff that models exponential, both decay and exponential growth and decay, right? So now we're going to decide if it appears to be linear, exponential, or neither, and then use the appropriate regression equation to do that. All right, so here's your first example. Scientists are studying the growth of a particular virus in a large community. The table below shows this case count after D days. So let's go ahead and make a scatter plot of the data. So I'm going to go ahead and pull up decimals.com and enter this data, and then look at the scatter plot. And then we'll decide if it looks like it's following a line or a curve for exponentials. So now I've got my data in. I don't see it, and so let me zoom out. Notice my x's go from 0 to 13. Let me go from like -1 up to I don't know, 14, 15 or so. Let me take my y's. Now my y's, the largest one is 484. So let me go like, I don't know, -10. Maybe I'll go up to 500 or so. Maybe I'll go -50. That's a little better. Take this. Yeah, that's fine. Let me zoom out a little bit more. And then I'm looking at that, and can you kind of see that curvature on that? A little bit. Right there, see that little lip on the right-hand side? Unfortunately, I can't draw on this. But you can kind of see with my mouse there. See how it's curving up here. All right. So I'm going to say, well, this is a exponential regression. So y1 tilde ab to the x1. Make sure you've got log mode on. And I'm going to steal that a and that b when I write this equation. So let's go back and answer our questions now. So it has some curvature to that. It was exponential, right? It followed a little bit more like that. We used the regression feature and we ended up with y equaling a is 181.18143 times b, which is 1.06881 to the x power. Let me put that in parentheses. And so this is our case count. And our for number of days, so D is our X on that. So here's part B on that. And then if D is 15, could we predict the case count? So C of 15, let's plug a 15 in. And this will end up being 492.9220324. So it's about 493. So after 15 days, the case count of the virus is about 493 cases in the community after 15 days, right? That's what it's saying. Now this time we've got a real estate company. They're tracking the number of calls they receive each month requesting information on homes. So like in the first month they had 1,204 calls and so on, right? So let's go ahead and put it into a scatter plot, take a look at it, see if it looks like it's following a line or exponential. I'm going to go ahead and pause it while I enter the data into decimals. All right, so I entered all my data. I don't see it. I could zoom out, but I'm going to be a little more precise with my window. I'm going to go from, let's say, -1 or so up to, notice my high value is 12. I'll go up to, I don't know, 14 or so. My Y values, on the other hand, the largest there looks like it's 5714. Let me go from like -100 up to like 6,000 or so. And you can kind of see, let me zoom out a little bit more. I don't know if that's the best window, but kind of, there we go. Now I'm looking at that and I'm like, well, gosh, I've got this stuff and I got this kind of weird stuff down here. This doesn't follow a line, nor does it follow a regression curve, does it? So I'm going to answer the question now. Does it appear to be linear, exponential, or neither? Well, this one's definitely neither. And so this would be not applicable. There's no regression equation to do on this. Got one more here, and this is showing the square footage as it relates to the price of the home in thousands of dollars, of course, in Scottsdale, Arizona. So we're going to go ahead and pull up our decimals again, enter that data into our graphing calculator. It was, let's see, 1517, 1790, 2315, 2940, oops, and 3300. That's the square feet of the homes. If it was square feet of the homes, it was a $399,000 home. 1790 square foot was a $433,000 home, and so on. And now I don't see the data, but let me go ahead and adjust my axis. Let's go from -100. It looks like my x's go up to that 3,300. Let's go up to like, I don't know, 3,700 or so. Maybe I'll go -500. Let's see how that looks. Yeah, that's not bad. And then now let's do our y's. The y's have a high of 576, it looks like. So let's go from like -100 to let's go at least up to 600 or so. And let's look at that data. Actually, let me zoom out a little bit more with the zoom out feature there. And you can kind of see how this follows a line there. It's more linear, right? Instead of some curvature. So I say, all right, this thing's linear. Let me go punch in y1 tilde mx1 for a line plus b. And let me make a note of my m and my b. And see that r right there, that correlation coefficient, that 0.9916, is very predictive, right? So it's a pretty strong positive relationship. So let's flip this over. Go back here and let's make note that yes, this is linear, follows a line, and we ended up with y equaling m 0.103517 x plus the b, which was 244.01617. So the price in thousands of dollars is 0.104 if I round that times its square footage s plus 244.016. There's our model. So price in terms of thousands of dollars is 0.104s plus 244.016. What would be the price of a home if it was a 3,450 square foot? Ooh, we are buying a nice home. This will end up being 602.816. Remember, this is in thousands, right? So a home in Scottsdale at the time of this data, Arizona, that is 3,450 square feet, would have a sale price cost you $602,816 at the time. Probably a lot more than that right now, I'm sure. Well, thanks so much for watching, and we'll see you next time.